This is the one-way ANOVA video on the details of the ANOVA table. As illustrated in another video, the ANOVA table is a method for presenting the calculations leading to a signal-to-noise ratio. The greater the signal relative to the level of noise, the lower the p-value, the more strongly significant is the model. The model sum of squares denotes the signal, and the error sum of squares denotes the noise. The total sum of squares denotes the amount of variability in the data. The ANOVA table illustrates the fundamental relationship that the total amount of variation in the outcome variable can be partitioned into signal and noise. This is an algebraic identity that we won't prove here. The signal is sometimes termed explained variation, with the noise termed unexplained variation. Only three quantities are required to create an ANOVA table. The observed value of the outcome will differ from observation to observation. There will be a single mean of that outcome variable for the entire data set. The predicted values will depend on the group, each observation within a group having the same predicted value. These same quantities will be required for ANOVA tables for more complex models. Indeed, the only thing that will change is the formula used to calculate the predicted value. This slide presents the formula for the three components of the ANOVA table. The summations extend across all the patients in the data set. Your statistical software will perform the calculations for you. You always have a default prediction, even if the group means don't differ. That is, you can always use the mean value of the outcome as your prediction. In that case, the model sum of squares is 0, and the error sum of squares equals the total sum of squares. The model sum of squares can't be negative, nor can the error sum of squares exceed the total. This slide illustrates the relationship between signal, noise, and model fit. How large the model sum of squares must be relative to the error sum of squares in order to be able to declare statistical significance is what the ANOVA table is all about. To get a signal-to-noise ratio, we first translate sum of squares into mean squares by dividing through by something called the degrees of freedom. This slide provides, if not a precise definition, at least an illustration of the idea behind degrees of freedom. These are the formula for degrees of freedom in the one-way ANOVA. The more groups, the more degrees of freedom are associated with the model. More generally, the more complex the model, the more degrees of freedom are associated with it. Once the mean squares are created, divide the model mean square, in other words the signal, by the error mean square, that is the noise, to create an F statistic. It should be intuitive. Large values of the F statistic represent statistical significance. The actual calculation of the p-value is based on the distribution of F statistics that would be expected under the null hypothesis. This is something called a central F distribution that has two parameters. The first is the degrees of freedom in the numerator, and the second is the degrees of freedom in the denominator. If this overall F test is statistically significant, some of the group means differ. The F test assesses whether the model as a whole is accounting for a larger amount of variation in the outcome than would be expected due to chance alone. In other words, whether any of the predictors in the model matter. Here the model only has a single predictor. The mean square error from the ANOVA table represents the amount of unexplained variation or noise in the system. Apart from being derivable from the formula for the sum of squares for error, the mean square for error also equals the weighted average of the variances of the groups, weighted by their sample sizes. R squared denotes the proportion of variation in the outcome explained by the model. Please note that its formula uses sums of squares rather than mean squares. R squared is bounded by 0 and 1. Good statistical practice includes reporting R squared in addition to the p-value associated with the overall F test. The negative reason is that for large data sets, statistical significance can be deceptive, and that even trivially predicted models will tend to be declared as statistically significant. The positive reason is that reporting R squared allows your audience to assess just how predictive your model is, and to compare your reported R squared statistic against discipline-specific benchmarks.